And I would like to welcome all of you to the last in a series of 4 webinars, short half-hour webinars, where I wanted to introduce to you the new release of the EMVA 1288 standard. Today, in the last seminar, we are basically going to put everything together. That means what we are trying to do is to really now use the data sheet. I will explain now the EMVA 1288 summary data sheet, in which all the figures we have learned about are summarized, which helps you for an easy camera comparison. And I will, of course, also use the knowledge we discussed yesterday about the applications. So what do you need to know? What are the really critical parameters for your application? We will put all these things together. So as I said, we will start with the standardized EMVA 1288 summary sheet and then do a simple practical camera comparison, bringing into the knowledge from yesterday. And then, of course, you always have the opportunity to ask some questions. Let me start with this summary data sheet, and this is actually a big progress which came to the 1288 standard only with release 3.1, so it was easier actually to discuss the physics of image sensors. There is not much to argue about, but it's a little bit harder to get now all the figures together and to especially to present them in a way that you can take a data sheet from vendor A and from vendor B and directly do the comparison. And this took a little bit more discussion in the working group. So what is on this interesting one-page thing? And since it's a sheet which I cannot put completely on one slide, I will show it to you in pieces. So let's start with the upper part, and there you will see a column which describes the operating point, as we call it. It includes what type of data are presented there. And typically, I would say in 95% or even more of the cases, you find simply the result of a single camera. Some vendors measure several cameras in one data sheet, so you get a good feeling of averages, or others might present guaranteed data. But the typical thing is single data. Then there is the next important issue with relation to your camera is the exposure time. The exposure control is actually some internal information how the radiation is changed. You can do this either by exposure time or by the intensity of your light source. And here, this is by the intensity of the light source. But what is important to compare is what exposure time is used, because you might use your camera with a different exposure time, and I will explain what might change if you change the exposure time. Then you will see the frame rate, data transfer mode. This is now a 12-bit camera, as you can see, with a packed data format. And then you see on the other side, you see the gain and the black level. So that is also of importance. Actually, this first table here with the operating point includes all the parameters so that the measurements can be repeated by everybody. You might say, oh, I know camera has so many other points. Well, if they are not listed here, it's factory default. For instance, let me give you one example. You might be interested to see how your camera performs in binning mode. And if you do a binning mode, you have, of course, to add this to this table here, because that is a deviation from the standard factory mode. Then the environmental temperature is noted, under which the temperatures are made, and also the camera body temperature. That's again important, especially for the dark current, because the question how hot the camera body gets depends how well it's connected to some heat sink. So if you may know if you leave these very small cameras, for instance, just without any connections, they might get quite hot. And so you can compare. If you want to measure the camera body of your temperature camera, as you use it in the application, you can compare how much it deviates from this measurement, and then you can see how well actually the heat is going away from the camera in your application. Sometimes there are also internal temperatures which you can read out of the camera. This was not the case here. And then an always important parameter is, of course, at which wavelengths you have done the measurements. This is a standard monochrome sensor which is measured with green light, here 53.4 nanometers and with 30.1 nanometer bandwidth. So that gives you basically how have the measurements been performed. Well, in the next step, what we see is, you see here one graph, and then on the right side, you see the parameters listed here. The first thing what is listed actually, that is actually a template, I forget that, a summary sheet still of 3.1. And I start with that because many data sheets are still available from 3.1, and you are certainly curious to learn how do the data sheets from the new version release 4.0 deviate from that. So let me start with this one, and then I will explain you later on the deviation. The phototransfer curve is one of the important curves to check whether a camera is really linear. In the phototransfer curve, you draw basically the variance of temporal variance as a function of the mean photo-induced gray value. And for a linear camera, this should be linear. You see, this is the case, except for the upper part. So the standard anyway does this linear regression only for 70%. And if there should be a deviation from this linear behavior, then it's a clear indication, be careful what parameters might not be accurate. I will come to that in a moment. So that is basically an indication, does the linear camera really fulfill the 1288 model? And it requires a linear phototransfer curve. Because out of the phototransfer curve, you basically estimate the overall system gain, which is shown here on the right in two figures. In dn per electron and in electrons per dn, so just the inverse. And we can get then, of course, if we add the characteristic curve, also the quantum efficiency. That is this linear model. So these two parameters, quantum efficiency and overall system gain, are two of the three parameters of a linear EMVA 1288 camera model. And then comes the temporal dark noise, which tells you how much noise is added by the camera. And this is given in 2 units. It is given as it is measured, which we call sigma y dot dark in dn. Here you see it's quite a low value, a little bit below 1 dn. And also if you look here in electrons, the dark noise is just a little bit more than 2 electrons. So actually a very excellent behavior. These are the basic 3 parameters of the model. They are put in the first place here because everything else then is based on these parameters. And now we come to the parameters in this column on the right side, which you are really interested for your application. We start with everything which has to do with temporal noise. And the signal-to-noise ratio is really the most important quantity for the quality of a signal. And it is shown here as a maximum SNR, which for a linear camera is always at close to saturation. You see the SNR is about 100, which means that the signal is 100 times larger than the standard deviation of the temporal noise, or the temporal noise is 1%, if you want to see it the other way around. Actually, there is also a 1 over SNR max plotted here, shown here, so that you also see how much percentage of temporal noise you have at the best point in your camera. Some people like to think more in dB, so the same SNR max can also be expressed as in dB, which is 40.3 dB, or some even prefer to convert this to a bit resolution. This is actually the log to the base 2 of 100, which is about 6.7 bit here. So that tells you how much the camera signal is spoiled by noise at the best point in the camera close to saturation. Then we want to know actually what is the smallest intensity we can measure, and that is expressed again in two quantities, in photons and in electrons. You see it's a little bit larger than the dark noise. This has to do with theory, but that is really the value where the noise is equal to the signal itself. So where the SNR is 1. This is a little bit larger than the dark noise. 2.86 electrons, or in photons. The ratio of this is of course just given by the quantum efficiency, because not every photon is converted into an electron here, only 65%, and this is why you need 65% more photons, and this is why the value in photons is important. We have also learned that if we take a lens and observe a scene and take a certain F number, what is actually the irradiation at the image plane? Well, it is basically given in watts per unit area. So actually, for a same F number, you have actually the same irradiance. And if you give the absolute sensitivity threshold in photons or in electrons, it is actually given per pixel. And if you want to compare now cameras with different pixel sizes, you might be missing the point if you just look for the photons and for the electrons, because the irradiation is photons per, and we explain it here as photons per square micrometer. So for comparison of image sensors under the condition of constant irradiance, the absolute threshold in photons per micrometer square or in electrons per micrometer square is more important. By the way, why do we give here photons and electrons? Electrons is what we measure, so that's universal. If you take the electron value and you know the camera, let's say in the infrared, has a quantum efficiency of 20%, then of course you can have to take the number of electrons multiplied by 5 to get then the photons for these wavelengths. A photon is specific for a certain wavelength. Electron is universal. So you can more easily convert it to other things. That is basically how you treat the absolute sensitivity threshold in photons and in electrons, and also per unit area. And the same, of course, is then true for a very important force parameter. You see that nicely in the photon transfer curve. Unfortunately, you can not measure very high irradiance because the camera comes into saturation. And so we have also the saturation capacity. And let me switch. Maybe I just leave it here because it's easier to handle it this way. The saturation capacity is again given in photons per square micrometer, and also, let me switch to the next slide, in electrons and in electrons per micrometer square. So then you can, out of these two figures, you see now also the second most important graph on this summary sheet is the SNR, because out of the SNR, we know the quality of the signal at each saturation level. From saturation where we have the highest, you see about 100, that was what the figures say, and SNR equal 1, this is here. On the left side, you see you need about, well, that is 2 2, 3, almost 3, a little bit more than 3 photons. Let me compare that with, oh no, 4, sorry, I was wrong, 4.38 photons. And if you look here, that's a logarithmic scale, it's 1, 2, 4, so it's a little bit more than 4. So you can, in the graph of the SNR, you can immediately see that. In addition, you can immediately see what's called the dynamic range. You know the highest irradiance we can measure, you know the lowest one in photons per pixel, and the ratio of the two is just what's called the dynamic range. And that is like the signal to noise ratio, so you can express it in a direct ratio, which is almost 4,000 in this case, or in dB or in bits again. So that was all derived parameters which you use for your practical applications, and you know exactly in which intensity range this camera can be used from saturation to SNR equal 1. And then you can compare directly cameras, which camera has a higher dynamic range or fits to the dynamic range actually your application requires. Then we have also the spatial non-uniformities. And there we have basically two things. We have what's called the dark signal non-uniformity, which is like the temporal dark noise and can directly be compared with the temporal dark noise, which is here 0.76 electrons or 0.28 dN. If you compare that with what is on the top here, on the top we had a dark temporal noise of a little bit more than 2 electrons and almost 1 dN dark temporal noise, and then you can nicely see that the DSNU is significantly lower. So in close for very dark images or very less light, the system is really dominated by the dark noise and temporal dark noise, sorry, and not the DSNU. For the PRNU, which is the question how many percents change the sensitivity of the pixels, that is about 0.5%. And if you compare that with the 1 over SNR, that's about 1%. So you can see that the PRNU is a little bit larger, but still not dominating. You can see that on the dashed line. The dashed line is a total SNR. It deviates only close to saturation a little bit. So again, this is a camera which is really dominated. The quality is dominated by temporal noise, and all the non-uniformities have actually been suppressed very well. So that is the question of non-uniformities. You have seen we have all that what you need to know about temporal noise and non-uniformities, and then we have two more parameters. For some applications, the linearity is critical, not for all, but for some. And in 3.1 we gave a deviation, negative and positive deviations. So that turned basically that this is not a very stable measurement. So we will see the change which is going to place in release 4.0. But this again gives you, if you just look at these figures, linearity far below 1% is already an excellent linearity of this camera. The final limitation comes then from the dark current. That means the question, how much dark signal do we get as a function of the exposure time? And here you can see that you can measure that with the mean and the variance. Often the dark current is suppressed so that you cannot see it in the mean, but you always see in the variance. So if the dark current for mean is not represented, that means it could not be measured, or it could also be negative, so it's simply wrong. And here you see, so let's look here in that case, actually the measurements are the same for a measurement from mean and the variance, so it's about 6 electrons per second. And here you can already see, oh yeah, what was actually the temporal noise? The temporal dark noise was only 2 electrons. And we did these measurements at 1 millisecond. If I would now do a measurement at 1 second, you see the dark current produces 6 electrons per second. So that means we get additional noise. And that means for higher exposure times, the noise in the dark is significantly larger. And that is also one thing you have to consider depending on your application. So if your application involves longer exposure times, be careful not to say here that the dark temporal noise is what I really have close in the dark, but be careful to look to add basically what you get from the dark current in addition. That is a very important issue to take into account. So with that, you have all the basic parameters. The whole EMVA 1288 datasheet contains much more detailed information, but that is really essential, which you can use as a user for a first investigation, which camera is the best. So now, if you see all these figures, the next important question is, how can I trust these figures? Because let's assume we have one camera which has a quantum efficiency of 65%, which results, of course, then in a corresponding absolute sensitivity threshold in photons and saturation capacity. And another camera would have a 5% lower quantum efficiency. That means the absolute sensitivity threshold goes up by 5%, and also the saturation capacity in photons would be a little bit larger, so it would be a little bit less sensitive. But the question is what is significant? That means how good can we trust all these numbers? The important issue here to learn is that basically each measurement has an absolute calibration error. And everything what contains photons depends on this absolute radiation calibration and also, of course, the quantum efficiency. And the accuracy of this calibration is typically 3 to 5%. That means if you have differences in this order of 5%, they are simply not significant. You cannot say the one or the other camera is better. So please keep into mind that this is not sufficient. All the other parameters you basically see here, like the SNR, like the dynamic range, these figures are typically much more precise. We did a lot of comparisons and they are typically in the 1% region. So the important take-home message is be careful with everything with photons that might be easily wrong by 5%, or they're accurate by 5%, and also the other parameters are typically in the order of 1%, to give you just a rule of thumb. So now there might also be possible systematic errors, especially if you have a nonlinear photon transfer curve that results in a too low system gain, and then we would get a too high quantum efficiency number, which is of course not very nice. And the best is, and we might also have another problem, if we have a 2-course digitization, typically an 8-bit sensor or an 8-bit resolution only with a good image sensor, we will not be able to measure the dark noise. So you cannot say anything about the dark noise, because then you always get the same value and cannot measure how large the dark noise really is. So that must be also masked in a data sheet if you cannot measure the dark noise. And those who are interested in all the detailed measurements will learn all the details how to do this. Just let me show you the question of the nonlinear photon transfer curve, that you get an idea. Here you see a curve, photon transfer curve, which also in the lower part shows some deviation here. And this curve actually gives you a quantum efficiency then of 69.5%. Oh, my screen is just again here. And so the question is, do we have a bias then in the estimate of the quantum efficiency? And a trick which typically good people who are well adapted to the 1288 standard, they know it, then they say the following: oh, I can do the following. I will make another measurements with a higher gain, because then the camera is more linear. and then check what I will get then. Then I get an idea basically how large the error is by this. And here you see the same camera measured at a higher gain, and now you see a perfectly linear photon transfer curve, and now you measure 86.5%, which is the first example. In the other way was a bias of about 1.6%. So that I just wanted to say you, if you see deviations in this order, it's still okay, because quantum efficiency anyway is, the absolute accuracy is only 3 to 5%. So deviations from the photon transfer curve in this order is fine. So, but the time is running. Let's go and see what is changing with release 4.0. With release 4.0, since we will basically have the very same operating point. So nothing is changing here. The summary data sheet looks the very same. So at first view, you cannot see is this release 4 or release 3.1. And so each data sheet now must include a comment or a line in this at the top here, which method has been used, so with release. So that is release 4.0 linear. Nothing changes with quantum efficiency and overall system gain, that we have still the same model. Nothing changes with temporal noise. Nothing changes with the photon transfer curve. But here now the first changes occur, and I did do it in such a way that I modified the 3.1 model so that you can see what is going to change. We no longer use bits, because that turned out to be used only by very few people. So that for SNR, the ratio and dB is sufficient, and also the 1 over SNR. Nothing is changing with the absolute sensitivity threshold and with the saturation capacity. And then with the dynamic range, we also leave out the bits. So that means completely consistent type of data for everything with temporal noise. The changes come now with the spatial non-uniformity for several reasons. The first thing is that we report only in electrons now, and the reason is we have split up DSNU and PRNU now not only in total values, but also in row, column, and pixel values. So for both the DSNU and the PRNU, instead of one value, we have 4 values to see whether the DSNU is rather just pixel by pixel variation, or whether it is a pattern in row or in column direction. And this is why we said, well, let's leave out the dn, because with a k, you can always compute to dn, and let's only put it with electrons. And then we have, instead of 2 of 3 values, we have 8 now. And now you might see the reason why we also kicked out the bits here in the dynamic range and in the SNR, because we needed some more space. The linearity error has been simplified. Instead of a maximum negative deviation and a maximum positive deviation, we changed to a simple, not standard deviation, but we took actually the mean of the absolute difference between the regression and the values. So we have one linearity error now, and this turned out to be a more consistent representation, and also easier to grasp than the min and the max. So that was one clear improvement we did with the linearity. Oh, I should also say one important change with the DSNU, with the PRNU is also taking place. We found with extensive comparisons that the PRNU of the cameras gets better and better. And so we finally started measuring basically the non-uniformity of the light source. Because the light source, remember, I have not said that, but the light source should be homogeneous better than 3%. But 3% is much more than the value you see here of 0.48%. And so it turned out in comparison rounds that with these modern sensors, we have more and more measuring the light source. And to avoid this problem, what we do is we do a high-pass filtering first, because actually what is important of the PRNU and also of the DSNU is not the gradual change, but what is really of importance is whether there are fast changes from pixel to pixel or from column to column or row to row. So we did a high pass filtering to avoid this problem. And therefore also these figures are now typically lower than with 3.1. So be not surprised if the cameras look better now with release 4 because we made a change here. For the dark current, we report only in electrons. For mean and variance, we no longer report, I didn't say that is an optional measurement, the doubling temperature, because it turned out that the dark current is much more complex for modern sensors. It's not simply a constant doubling temperature, but if the temperature is going lower, the dark current may not change at all. But other than that, you see, we have the very same thing in this data sheet. Then let's go to the channel model where we do not make any assumption about linearity. And let me just go here again. What is if we have no linear camera and even do not know that photons are converted to electrons, what is the problem we have? Well, we do not no longer know this basic two, out of the three parameters, we no longer know the quantum efficiency and the overall system gain, because that is for a linear model here. We still know, of course, the temporal dark noise. The next problem is, since we have no gain of the camera, we cannot express anything in electrons anymore. So what you see then in the channel, the datasheet for the channel model, there is no, the quantum efficiency is still listed, but is said that it's not applicable to measure absolute quantum efficiencies. You still can measure, of course, relative quantum efficiencies, and this is also reported. You can no longer measure the overall system gain. That's also not applicable. And everything what is an electron is simply changed to photons. So we basically have then everything here now reported instead of electrons in photons. Since we, for the absolute sensitivity threshold and saturation capacity, we anyway have it in this way, this is actually not a big deal at all. And also for the spatial non-uniformity, it's of course no longer in electrons, but in photons. For the P and U, nothing is changing. Linearity, of course, is also not reported because in general, we have no linear characteristic curve for the very channel model. So you see that powerful summary sheet from 3.1 works also very well for the new release. And the interesting thing is, again, the SNR is of course of importance, so this will be kept. And you can also simply compare, because the SNR is the most essential parameter. It includes temporal noise and also it includes the spatial non-uniformity. You can compare then even nonlinear and linear cameras with the SNR. By the way, I forget one thing. The photon transfer curve is also no longer listed in the channel one. We use a characteristic curve here. That means we can immediately see what type of nonlinearity a channel camera has. Okay, I hope that this gave you a good understanding of here's just summarized again the changes of the datasheet 4.0 general. How the datasheet is, the summary datasheet is built up. And now to find a quick final application of that, let's simply now ask ourselves, given what we discussed yesterday, what are now for your application the most important issues and which parameters to look at? And as I said already yesterday, there is no best camera per se. You have always to look basically for your application, what scene irradiance you have, how much dynamic range is required for your application, what exposure times you are using, or you can tolerate if you have moving object, and also what SNR is actually required so that your image processing is working. That could be a threshold, or you would like to be as good as possible. And then let's simply use that now for application, for 2 or 3 application examples. Let's assume we have really plenty of light. Well, then it's very easy. Then we even do not take care of the quantum efficiency. We can always produce enough electrons because we have so many photons available. And so the only thing which governs basically the quality of our signal is how large the maximum SNR is. So that is really the critical parameter then. And you should, of course, check this not only for temporal noise, but also for the spatial non-uniformity. That means carefully check also for the total SNR for additional influences of the non-uniformity from the PRNU. That's the easy situation, because then you can basically only look for this parameter. For dark scenes and short exposure times, the critical parameter is the smallest sensitivity threshold, and this is just the equation how the sensitivity threshold is related to the dark current, to the temporal dark noise. And then, of course, the temporal dark noise is a real critical issue in that case. The minimum irradiance, that's important here to add as well, depends also on the pixel area. So here we are actually in the bad situation that if we really want to measure very low irradiances, we need to have large pixels, because the area is down here in this equation. So if we have a pixel with a double size, we simply get 4 times more electrons and a better signal. And as I said, this is a bad choice in that sense, because sensors with large pixels are more expensive. So that is might be a problem if you have really dark scenes or short exposure times. And if you have dark scenes and long exposure times, then the critical parameter is actually the smallest dark current, because that limits then how your image looks like. And I have for reference also the equation here. And finally, one of the most difficult cases where you have to take most effort to select really the best possible camera is if you have a scene in which in the same image you have quite dark parts and quite bright parts. That means a high dynamic range scene. Then the critical parameter is both the sensitivity threshold and the saturation capacity, and you need a high dynamic range. I hope that these thoughts help you to connect now everything. You have the data sheet, you know your application, and then out of your application, pick out those parameters which are most important, and then look into the data sheet for the comparison. So let me thank you again for participating. I think most of you really stayed tuned for all the 4 half-hour seminars. And the next opportunity, as I said already, is what you could do is you can become a certified EMVA user or expert. The next opportunity, you can get the standard deviations, the documents all from the net. You can download the slides. In that sense, thank you very much again to all of you. And I wish you a nice day and look forward to meeting you again, either in an online seminar or in person at one or the other occasion. Thank you very much for your attention.